Hello, this is Jason Kendall, and welcome to yet another one of my introductory astronomy lectures. Last time I introduced Newton's laws, and I said all sorts of crazy things like equations like F equals ma and gmm over r squared, and showed them to you over on the side of the screen. But sometimes when people look at this stuff, they get terrified. So I want to actually get rid of that terror about equations and tell you what they are. So equations are really just shorthand versions of sentences, of very long sentences. So let's actually look at one of the fiducial equations that we saw last time, which is F equals ma. Okay, so now anyone who looks at this thing would say, oh, F equals ma. What's ma? Well, that's clearly not the way to write it. So F equals ma is just an extreme shorthand for what we talk about. So each of these things has a definition, right? So when we talk about m, we're talking about the mass of an object. The a is the acceleration, and f is the force. And so that's the definition of a thing. So really, these are shorthand notations. And when we say this, we'd say the force is defined to be a mass that is accelerated, or a force is that which accelerates a mass. That's another way of saying this equation. So, well, what does that actually mean? I mean, the thing is that science is about measurement. So when we talk about measurement, measurement is the key to everything. And so we have to say, well, what the heck are we measuring? Okay, acceleration is a change in speed. All right, so what is an acceleration? So we say acceleration is change in speed. So what do we mean by change in speed? This silly thing is not working as well as I need, so I'll go to that one. So acceleration is a change in speed. So we would say well, what's a change in speed? Well, speed, change in speed, is a distance divided by a time. A distance divided by a time is a speed. All right, so if we then say a distance divided by a time, how that changes with time, we would say a distance divided by a time divided by a time. That's really clumsy, but that's what an acceleration is. It is a distance divided by time divided by time. Again, what do we mean by that? Well, let's say we have a speed. We'll call it speed 1. Go speed racer. Speed 1, and then we end at speed 2. So there's our beginning speed is speed 1, our ending speed is speed 2. Now then, we might have started our clock at clock 1, clock time 1, and we would have ended our time at clock time 2. Wow, well this kind of helps us understand what we're doing. So speed 1, speed 2, we want to compare the change in speed over the change in time. So we'd say, well, take speed 1 and subtract speed 2 from it. Now, if speed 2 is slower, we're decelerating. Well, in this case, let's say we're accelerating, then speed 2 would be bigger than speed 1. I mean, it doesn't really matter. If it's the negative sign, wherever it appears, just you have to remember it and follow it. So let's say speed 1 is lower than speed 2, right? So we end with a bigger number, so it's a bigger negative number. It's just going to be kind of weird, but let's see what happens though. So, and if then time 1 minus time 2. So those are our two times. So if we start from a small speed and go to a big speed, we get a big negative number. But time is like we start at 10 seconds and maybe we end at 15 seconds. So that's a negative number, so they cancel. So the difference in speed divided by the difference in time, that's an acceleration. Now, whether it's accelerating or decelerating, we really don't care. So difference in speeds divided by difference in times gives us an acceleration. All right, so what does that mean even still? So we're going to get back to this F equals ma. We're going to try to interpret it. So here we go. But let's use this. Now, when we talk about speeds, when we talk about times, we have two sets of units for distance and time. They're two different things. Now, when we talk about Einstein later, we're going to make sure they're the same, but wait for that. So distance is a fundamental thing. And when we talk about distance, we might use meters. Okay, meters for distance. And time, we might use seconds, right? So a speed is simply a meters per second because it's a distance in a time. So what's the distance per time? It's meters per second. So a speed is meters per second. And a time is per second. So the units, that's weird. The units of speed. Units of speed. When we talk about units, we mean what we're measuring it in. We can measure speeds in meters per second, kilometers per hour, kilometers per second, miles per hour. That's a measurement of speed. And acceleration is speed per second, or miles per second, or meters per second, or kilometers per hour per second. That's a weird unit. But that's when we say, like you'd see a car commercial and they say, oh, this car can accelerate from 0 to 60 in 5 seconds. That's 60 kilometers per hour. It goes to 60 miles per hour in 5 seconds. It's 60 miles per hour per 5 seconds, which means it's, what does that work out to be? 12 miles per hour per second, which is kind of a weird unit of acceleration, but it is a unit of acceleration because it's a distance per time. So what do we have then for distance? Units of distance then are distance divided by time, or we can just say meters per second, because that's our standard. Our standard is the SI units, which are the Système International, or SI. So meters per second is a standard unit. So 1 meter per second is a speed of 1 meter per second. 60 miles per hour is miles per hour. We convert miles to meters and hours to seconds if we want. But let's just keep it simple and use meters and seconds. So an acceleration is meters per second per second. So that's meters per second squared. Exponents. So the units of acceleration are distance per time. I like to say it like that. The units of acceleration, what we measure in acceleration, are distance per time, or we can say meters per second squared. You notice what I did there? Here's a scary thought. The units of acceleration are in meters, which is meters, and seconds, which is seconds. Meters are meters, which is a distance unit. Seconds are a time unit. But look at F equals ma. What's that m? M is mass. Oh, we're going to drive people crazy. We mix up units and definitions. So we have to be careful. We have to be very careful. Every number has a unit associated with it in science. If you make a measurement, you make a measurement with some kind of unit. So we were talking about distances. Okay, we can say that a speed might be 60 meters per second. So there's a 60 m divided by s, 60 meters per second. So if we have 60 meters per second, then that's our speed. But notice the m in meters is not the same as the m in F equals ma. I know, that's annoying. But guess what? We got to live with it, and we got to learn when we use an m as mass and when we use an m as meters. All right, so in a general equation like this, where there's no numbers attached to it, generally in equations, the letters in it can be independently multiplied together. This is mass times acceleration, not the word ma. Mass times acceleration with the star, with the cross for multiplication implied. So F stands for the word force. M here stands for the word mass, and here is this. And when we use this, we call this Newton's law of acceleration. But when we use this, we're making a measurement of speed. So we might say speed equals, right? So we say speed equals 60 meters per second. And we'd say, wait a second, we're going to vary from 60 meters per second up to 200 meters per second over the course of 5 seconds. So the acceleration would be 120 meters per second minus 60 meters per second divided by, maybe we do that in 10 seconds, and 10 seconds in terms of 10 seconds. So then we end up with 6 meters per second squared, because the seconds go on the bottom, and that's how the algebra works, is that these seconds go to the bottom, that second goes to the bottom, they're a product, and we get a set meters per second squared. So the end result is that the units have an m and an s squared, but the m is shorthand for meters, and this s is shorthand for seconds, and that is not the shorthand for meters. That's the shorthand for mass. So these are separate objects. Notice this is not a measurement. F equals ma is not a measurement. It is a statement of relationship. Whereas this is a statement of measurement. Speed equals 60 meters per second. So if we have some statement of measurement, there shall always be some units associated with it. The standard units for almost all the measurements that we're going to be talking about in the system is SI units. The distance of the unit of distance is the meter, which is abbreviated with a little letter m. There's also a derived unit from it, which is the kilometer, which has the abbreviation km. So there's two letters together. And it doesn't mean it's k times m, it means it's kilometer, which is an abbreviation for a unit. So we don't use kilometers in here or anything like that. That's not a statement of relationship. This is a statement of relationship when the F equals ma. But now I'm talking about statements of units, which are when you take a measurement. So you might measure a distance in kilometers, but you're not going to always write out the word kilometers, right? So you write the little letter km. All right, we've also have other measurements of distance, such as the astronomical unit, which is a huge number of kilometers. It's 150 million kilometers. Now, 150 million kilometers is a long way. And we don't want to always write that out when we're talking about the distance between the Earth and the Sun, or between Jupiter and Saturn, or between Saturn and the Sun, or between the Earth and the Sun and Pluto. We don't want to write 600 million billion kilometers or whatever it has to be. We want to just say, for distance to the Sun is 9 astronomical units. The distance to Neptune is 40 astronomical units, or whatever it happens to be. So that's what we want to focus on, is those easy to use units. You use the units that are easiest to use, but that doesn't change the relationship. F equals ma is a relationship between forces, masses, and accelerations. You can use whatever units you want in acceleration. You can use whatever units you want in mass. There's a standard unit for force, so you might as well use it. And therefore, your unit of mass that we use is called the kilogram, not the gram. The gram is about as much as a paper clip or two, or a penny or two. But the unit of mass is the kilogram. The unit of distance is the meter, the standard unit of distance, and the standard unit of time is the second. So those three things give us pretty much everything we want. Everything else is derived from them. So distance is a fundamental measurement, time is a fundamental measurement, mass is a fundamental measurement, speed is not. Speed is derived by taking a distance over time, measuring a distance through time, like how fast are you going? An acceleration is how fast do you change how fast you're going through time. That is a derived measurement based on distance and times. So then we can say, well, if we take a given mass of a certain number of kilograms and accelerate it, we must have been applying a certain amount of force. So if we take 10 kilograms and accelerate it 60 meters per second squared, right? So 10 times 60 is 600. We must have applied a force of, what's the unit of force? Well, because Sir Isaac Newton developed the concept, we call the unit of force a Newton. So 1 Newton is called a kilogram times a meter divided by a second squared. It's a very strange unit. Remember, this is a mass times an acceleration. So masses are in kilograms and accelerations are meters per second squared. So when we look at the nature of what a force is, the force in terms of units is meters per second squared. Now we can have another derived unit, and that could be called energy. Now there's a lot of woo-woo stuff about the word energy, and what is energy? Energy is this and that, and it creates us, it forces, the force binds the galaxy together, whatever. But energy as a thing is an odd concept, but we can define it fairly simply for our uses in the material world, because what we want to do is want to see how much energy does it take to exert a force. Because when you exert a force, notice that if you exert a force and let's say you're pushing something up a hill, you're using a lot of force. Now, where does the force come from? the act of accelerating a mass through a distance means that you're exerting you're exerting energy. So exerting a force and using energy. So energy is being applied from one thing and being used to do another thing. So energy has an interesting set of units. It's kind of like this, but energy is force times distance. So a force applied through a distance is a unit of energy. So if you remember last time we talked about pushing cars across the ice, so you have a force pushing it, maybe you actually get the car to move a few meters, and it accelerates over the course of a couple of meters. Over the course of 2 meters, you accelerated from 0 to 1 meter per second. You're doing a pretty good job if you do that. You accelerate a car from 0 to 1 meter per second on ice over the course of, say, 2 meters. You hit it pretty hard, I think. You probably did. So the energy that it took is 2 meters, which is the distance through which you applied the force, times the force that you did, which is a mass, the mass of the car, whatever it happens to be, big, maybe 2,000 kilograms or 4,000 kilograms, a 2-ton truck. So 4,000 kilograms times the acceleration, which is 1 meter per second squared, times the distance through which you did that, which is 2 meters. And that's kind of a weird thing. So let's write that out so we see what we have. And let's see, I hope this is all actually getting read on there. Find out, we're going to replay. So if you have energy through an energy is applied by a force, or we will call this particular kind of energy work. And work is defined very specifically, meaning you take a force and you apply it, you multiply it by the distance through which you do it. So you take a force and you push something for a certain length of distance. Now, that's kind of an interesting way of thinking about it. It's a force applied through a distance. So you could say, well, I'm pushing on the truck and I have to keep my hands in contact with the truck. How far did I go while I did that? And that was 2 meters. So the force that I exerted on the truck was 2,000 kilograms that I accelerated for up to 2 meters per second. And I'm sorry, I said 1 meter per second, right? 1 meter per second. And I applied that force for 2 meters. So I went like this. So the length across here is about 2 meters. I pushed, released. So as I push on it for 2 meters. The car is, well, now it's a little car. It's only a little bit more mass than a smart car. 2,000 kilograms. And I accelerated it at the end of the acceleration. It was accelerated 1 meter per second. So 1 meter per second, sorry. So I accelerated it 1 meter per second squared. And at the end of, I kept that push happening for 2 meters. Now that's a heavy push. That's a really big push if you think about it. If we multiply that all out, that works out to be, whatever the units are, is 4,000 of something that has the units of kilograms times meters squared divided by seconds squared. Now that's interesting. So there's a mass in there, there's 2 distances, and there's 2 times. Kilograms times meters per squared divided by seconds squared. If we look closely, that looks like a mass, which I'm now going to do in capital M just to say it's a mass. I'll just write the word mass. Times a speed squared, times the square of a speed. So another way to think about it is, now that the car is moving, I've pushed it with that movement, now it's sliding across the ice. It has energy of motion. How much energy of motion? Well, how fast is it going? It's now going 1 meter per second because that's the acceleration that I pushed it up to. Well, I went 2 meters. I don't know how long it took for me to do that. So let's assume at the end it was going 1 meter per second. If I applied my distance for 1 second across it. So let's say it's going 1 meter per second, and that's the total energy it ends up with. And so therefore its speed is 1 meter per second squared, which is 1 meter squared per second squared, and times its mass, which is 2,000 kilograms. it now has a lot of speed. It has an energy according to its speed. And if you don't believe that, just let it hit you. So you get out of the way of a car sliding towards you, because when it hits you with a lot of energy. So energy is this thing that we call the thing that can make things move. It's an odd way of thinking about it. Energy is a thing that can cause forces to be acted. It is also a thing that causes motion. It is also something that possesses, that you have when you possess relative motion. Like if you're right beside the car, both you and the car have energy, but you're right next to it. Or maybe you're inside the car. Do you have energy with respect to the car inside the car? When you finally hit the other side of the lake from that icy lake, yeah, you're going to feel it. But the point is that energy of motion, which we call kinetic energy, is energy of motion, is mass times the speed squared, but there's also energy which we call work, which is applying a force through a distance. So there's these funny things. So to summarize this little bit, we have two ways of looking at equations. The first one is there's an expression of relationship, force equals mass times acceleration. Another expression that we learned last time was the expression due to the force of gravity. And how does that look? Well, the force due to gravity, which is a special kind of force, and so we always put a little sub g underneath it for gravity, that is equal to some big number, capital G, times the mass of one object, times the mass of the other object, divided by their distance, divided by the distance between them, squared. So now I've used new letters, haven't I? But yet remember, as I was writing it, I was giving you a description of each of them. I called this a force. I said the force due to gravity is defined to be, and that's what the equal sign means. It means it's defined to be some number, big G, which is an experimentally verified number. You can't derive it from anything. It's just a number of nature. It's the relation, it's how the masses translate into a force. So if you have some mass, say the mass of the Earth, and you have some other mass, say mass of you. You are pulling on the Earth and the Earth is pulling on you. So between you and the Earth, and what's the distance between the center of your mass, which is somewhere in the middle of your gut, and the center of the Earth, which is thousands of miles below you. So mass of you, mass of the Earth, divided by the distance between your centers of mass, times this mystical, magical, weirdo number, capital G, which is derivable only by seeing the acceleration, knowing the distance, and knowing the masses accurately. Can we get this gravitational number, which is a constant of nature? So this is a measurable, meaning the mass. This is also a measurable, meaning the mass. This is a distance, which is a measurable. And this is a force. So remember, a force is equal to a mass times an acceleration. But on the other side, we've just got two masses and a distance. So this crazy number G takes care of the rest of the units. So it has very strange units that convert mass times mass divided by distance squared into a mass times an acceleration. So units are important. When we say units, we mean how we measured the number we're talking about. And in math, if you're doing a regular math class, units are not important, because in geometry they are, but in just like algebra, like ninth grade algebra, you don't necessarily attach units onto solving equations like y equals x squared plus 4x minus 2 or something like that. You don't propagate the units up there. You're just finding the relationship between x and y in the algebra class. But in everything in science, no matter what we do, we must associate with every number we measure what it is we're measuring. We're measuring kilograms, we're measuring meters, we're measuring meters per second squared, we're measuring pounds of force. If a pound is a unit of force, which is the gravitational force. So anything that we measure with a unit, and in science there always is a unit attached to a number, always. There are some numbers that are unitless, which are very strange, but yet they're associated with the sciences, and they're conversion factors between one set of units and another, or they actually play into a measuring system. But in every possible measurement, everything that we measure has a unit, no matter what. So that's science. It has, we say, this number of things, like 12 oranges. That's a measurement of how many oranges you got. So in science, we have expressions of relationship. F equals ma, gmm over d squared. These are expressions of relationship, how a force is defined, how the gravitational force is defined. Those are expressions of relationship. And then we have a different kind of thing, which is the solution of the relationship given measurements. So we measured the amount of force. We can actually get the force measurement from, like, say, let's say we go to the model rocketry store and we get model rockets. I did that when I was a kid. A lot of fun. Get a model rocket. It tells you how many newtons of thrust it has. And you attach that in there and says, oh, it's how many newtons of thrust. And it shoots when you ignite it. Maybe the rocket will blast and keep blasting. And maybe we'll see how much energy it emits by when the rocket goes. Not just how long it takes for it to ride, but how far it pushes. And that'll determine the output of energy that it had. Or we can say, how fast is it going when it gets up to its maximum energy? So it went from 0 to 60, say, or whatever, how fast it goes. And so the mass of the object that's been accelerated and now it's going at speed has acquired energy. And so we manipulate both of these. And here's the trick. We manipulate both of them using the laws of algebra. So that 9th grade algebra thing, whether we're talking about relationships between equations, meaning fundamental relationships, what is a mass times acceleration, or different kinds of forces. There will be lots of other equations in science, and we're only going to talk about for this class, for this set of lectures, only a very few numbers of them. But these expressions of relationship follow the same rules of algebra as when we multiply numbers together. And in fact, if you looked really carefully, you'll notice that I applied the same rules of algebra to units. I have a mass times a mass, so I've got a mass squared. That's m times m. Well, m is meters, not masses. So when I took a meter measurement, a distance measurement, and I said, okay, meters times meters is meters squared. That's algebra again. So we can apply algebraic principles to unit measurements in the same way that we apply algebraic principles to these as well. They're linked, they use the same ideas, but your problem that you're going to always find in science, no matter how you do it, is trying to say, break yourself away. It's very difficult for a lot of people to do. And for me too, for a long time, it was tough. Because, I like to read, and I read a lot of different things. So when I read this, I would say F equals ma. Well, it's not ma. It is a force is defined to be something that accelerates a mass. Every equation that states a relationship is a shorthand thing for a long paragraph of chatting. So when we talk about Newton's law of gravity, again, it's a relationship that describes that defines how the force due to gravity operates. So the force that accelerates a mass is defined to be the product of the two masses that are gravitating divided by their distance squared. So that's the definition in words. So you don't read an equation like ddmr squared or something weird like that. You read it as a sentence or as a short paragraph. They're shorthand equations. So in that sense, equations are very much like shorthand, like a stenographer would write when they're trying to write really fast things, and say like a court stenographer. They have a shorthand notation that is defined sets of words that define shorthand notation that defines words and paragraphs and whole sentences. So in that sense, this is a very beginning idea. I just want to give you a cautionary way of thinking about it and saying that there are equations and every measurement has units and every unit has values. So I'll show you where you can actually derive those things at the end of the video. Hopefully I actually remember to do that. So at the end of the video, I'll show you a place where you can actually go see many of these things, and I'll show you a bunch of Wikipedia pages that are worth looking at. So we'll see you next time.